Hi, this is Maggie. In this video, we're going to look at the principles of object-oriented design outlined in Chapter 0 of the open source textbook Java, 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 Object-Oriented Problem Solving by Morelli, Walde, and Hoffman. At the time that I'm recording this video, the principles are in section 0.8.8, and they are the divide and conquer principle, the encapsulation principle, the interface principle, the information hiding principle, the generality principle, the extensibility principle, and the abstraction principle. Now first, we use principles to guide our software practices. There are many principles that we might use to evaluate our work at different levels. These principles apply to software design, and they represent one perspective, and perhaps include principles that another software developer might group together, or there might be principles missing here that another software developer thinks should be included. What we are going to do is take these principles and work to understand them and to apply them to our own work. When we have fully understood them and seen them at work in context, then we can evaluate how useful they are to us and whether we think we need to modify them. Our first job is to get a basic understanding of them so we can apply them to our work. So I'm going to discuss each of the principles in the context of an example, and I will try to describe how the example might be designed if the principle were followed versus if the principle were abandoned. The software example we'll consider is an application that has the following functionalities. 1, it can generate art based on a phrase obtained from the user. This art might be AI generated, but we will not concern ourselves with the implementation details. It can also generate art from a previously generated image. 2, it can manage user accounts. 3, it can manage a gallery of generated art in a user account, allowing the user to view the art, delete the art, favorite the art, and ask for new art to be generated from a work of art. 4, it can allow the user to edit their art. To start, editing will be fairly simple, but this might be extended in the future to very sophisticated image editing techniques. You may have seen software like this on the internet. Let's think about how a system like this might be designed and implemented, and we'll apply the 7 principles to each design. The first principle listed is the divide and conquer principle. The description is, generally, we will divide solutions to problems into sets of interacting objects, each with its own specialized tasks. I listed 4 pretty distinct functionalities for our software. So for the divide and conquer principle, we might imagine a system that has 4 different classes for each of the responsibilities. I've drawn a very simple diagram here of the 4 classes I propose. User account, with the responsibility of managing a user account. Art generator, with the responsibility of generating art from a phrase. Gallery, which maintains a gallery of images and allows the user to browse them in the ways described. And art editor, which allows the user to edit art. In addition to those 4 classes, we might also need a class to represent a piece of art, which I will call art, and a class to manage obtaining a phrase from the user, which I will call phrase interface. We will need a class to manage all user accounts as well, including adding, deleting, and suspending, and we'll call that account manager. Now these are very simple class diagrams showing only the name and a brief overview of class responsibilities. Sometimes when we are starting to create a design, and the design is in a high state of flux as we work through design decisions, we don't have more detail than this. Also note that I've drawn art in the middle of the other classes, as most of them will likely interact with art in some way. And I've drawn the phrase interface over near the art generator, as it will likely only collaborate with that object. And I've drawn the account manager near user account. So that is a first attempt at decomposing this problem using the divide and conquer principle. The opposite approach is to simply not, really, to have one monolithic class, and if we want to really avoid any divide and conquer designing, that monolithic class would have only one main method. If you've written programs of any size at all, you can imagine how complex they would be if you used no methods. Or if you've written object-oriented designs, maybe you can imagine putting all responsibilities into one class. It becomes complex, because when you're writing code related to one responsibility, you must consider all responsibilities and state data related to other responsibilities. The next principle is the encapsulation principle. The text says, each object will encapsulate the expertise, attributes, and actions that it needs to carry out its role in the solution. For our problem, let's consider one of the classes we've identified, the gallery class. This class will need to have access to the user's collection of art. It is an interface class, so it will need to have GUI objects and methods, such as a window that responds to user-generated events like clicks, and probably some buttons and menus. It will need algorithms that allow searching and sequentially accessing the art, as well as a way to keep track of what is currently being shown and what art, if any, the user has selected. What is important here is that the class is responsible for maintaining its data in a stable state such that it can always respond appropriately to messages. It is responsible for transforming its own state. If we do not follow the encapsulation principle, then I suppose the opposite is distribution. The art collection, interface, searching, accessing, and selecting are not all encapsulated in one class or object with the responsibility of managing the user's collection of art. I have seen beginners design classes in a way that violates this principle, such that they were completely dependent on their methods being called in a particular order by an outside entity. If the methods were called out of order, the program would crash. So I've seen classes designed as part of a functional decomposition of a problem. If we created a similarly designed version of the gallery class that violates this principle, it might have a method called showArt, in which it is sent the art to show. That must be called before the method called selectArt, in which it is set the location of a click. If selectArt is called before showArt, the program would crash. The object, rather than being encapsulated and an independent entity, is dependent on other parts of the system to drive it. The next principle is the interface principle, which states that each object will present an interface to other objects that will limit the way they interact with each other. I want to note here that these principles are all related, and this principle is strongly related to encapsulation and information hiding, which we haven't discussed yet. But let's consider our design, which we might give to 7 different teams to implement. Imagine you are tasked with implementing the gallery class. Not only will you need to know the public interface of classes in whatever GUI library you plan to use, but you will also need to know how to interact with a user account and how to interact with an art object. Otherwise, you might write an implementation that depends on the art object having a method that draws itself to the screen called draw, for example, with parameters of an XY location, and later you might discover that the developers of the art object didn't implement anything like that at all, because they can't read minds. All of the public interface of a class has to be defined before implementation, so developers know what to implement, and so they know exactly how their methods will collaborate with other objects to accomplish their responsibilities. One way this is done is by drawing sequence diagrams for all of the use cases for a system. Use cases are a UML method for specifying software requirements, which involves describing sequences of actions between an actor outside of the system being specified and the system itself. For example, if we have a use case called user displays their gallery, we might determine that this will involve the user account, gallery, and art classes. We list the messages that will be sent between these objects in order and showing the data passed in order to accomplish the system functionality. Those messages then become part of the public interface of each class. The user account object might send the gallery object the show message, passing a reference to its collection. The gallery object might then send a get thumbnail message to each art object in the collection, or to as many art objects that can fit in the gallery window. Now the gallery implementation team knows to create a public show method that takes a collection parameter, and they know exactly how to interact with the other objects to implement the method. The next principle is the information hiding principle, which states that objects will be designed to hide certain information and implementation details from other objects. Think of object data and implementation details as need to know, and decide on exactly what ways object data can be transformed, and allow those transformations only. As a general rule, make implementation details private, as implementation details might change. For example, we've already specified a get thumbnail message as part of the art class, but we don't know how it works, and how it works might change in the future if a better image scaling algorithm is developed. What we don't want to do is allow an outside object access to the raw image data for 2 reasons. One is we may store that raw image data differently in the future, and if we change that implementation and allowed any object access to it, then all code that relied on that implementation will be broken when we make the change. The other reason is there is a chance the raw data could get corrupted. For example, if an outside object decided to scale the image in place, replacing the old raw data with a version containing less information. We don't want this. We want to be able to look at the class methods and through those methods understand exactly how the object's data is transformed, what is allowed and what isn't. If, then, we find that the raw data is getting corrupted, we know we only need to debug the methods of the art class because we haven't granted external direct access to the implementation. I want to skip to the abstraction principle because I think the other 2 are somewhat special case principles that I would like to leave to the end. The abstraction principle states that the objects we design will be abstractions because they will ignore many of the attributes and actions that characterize the real objects they represent. They will include only those attributes and behaviors needed to solve a particular problem. Let's pause just a moment here. I know I said I want us to understand and apply these principles, but I do want to push back a little against the idea that software objects in an object-oriented system represent real-world objects. They certainly might, and we can apply this principle whenever that is the case. But they might not. They might be a new invention designed to solve a particular software problem. In a way, yes, everything is a metaphor. Everything is an abstraction of the physical. But an object that models a user really is representing a real-world entity, a human user, whereas an object that is a component of a design pattern, like an iterator, I think is something invented specifically to work with programmatic collection types, and I don't think it's very closely patterned after a real-world entity. My compromise here is to say that objects in an object-oriented system represent real-world entities to some degree, but in some cases to such a small degree that we don't really consider them that way. Okay, that said, I think the best example in our system is the user account, which will represent some aspects of a user, such as email address and possibly name, but it won't include most information about a real-world user, such as hair color, age, or what they ate for lunch. These attributes aren't relevant to our program. Back in the early days of graphical user interfaces, some software companies went overboard with desktop and painting metaphors to the point that the software was cumbersome to use, such as requiring the user to flip through files in a folder rather than displaying them all in a window, or requiring the user to physically position measuring devices in a drawing window. We were just learning back then, and we can all learn principles from mistakes made. Moving on, the generality principle states objects will be designed as generally as possible, so that rather than solving only a particular problem, they can solve similar problems of the same kind. We will make use of libraries in developing this software, libraries that were designed to be general so that they can be reused. We won't reinvent the wheel. So image representation, image editing, and GUI components will be available to us, and we'll most likely be able to build the art editor, gallery, and phrase interface classes by reusing these components. For our system, we should make our classes more general if there are ways in which we anticipate reusing them, perhaps in other programs or for future functionality in this program. For example, we might find the image editor or gallery are classes that we want to reuse if we write software that allows the user to view and enhance their own photos. We should be careful to focus on the problem before us and not spend resources over-designing for scenarios that are unlikely to come to pass. The final principle is the extensibility principle, which states objects will be designed so that they can potentially be extended to perform related tasks. Like the generality principle, the extensibility principle applies to library classes. We might extend GUI components like windows and buttons to include new functionality. We'll be able to do this without breaking any existing code that works with the components because of inheritance mechanisms built into Java. In my experience designing for extensibility in object-oriented systems, you want to provide an external interface that will allow the implementation to change without any need for change to the interface. That way we can extend the object and write a different implementation that still interacts with the outside world in the same way. For example, in our system, we might write the user account class to have a method called update credits, which would check the date against the date the user joined the site and update their image credits if another month had passed. We could then extend the system to include a super user account, a person who pays a monthly fee or generates example images for the site or performs some other service, who gets double the credits every month. We wouldn't need to change anything about the system except to write a new update credits method for the super user account. Contrast this with a system that sends an update credits message and passes in the number of credits. This is less extensible because it requires the external system to know how many credits the user gets, rather than locating this knowledge within the user account object. That might also be a correct design choice, but it would probably make more sense to allow the system to make overall adjustments in other ways, such as having a change credit amount message that gives the user account new data, but still gives the user account control over the data most of the time. That is an example that illustrates design choices that follow and that violate the principles outlined in Chapter 0 of Java. If you are just learning object-oriented design, as I assume you are, then these might feel difficult to distinguish, and some of my discussion of design decisions may have made no sense. Don't worry about that. Keep learning and practicing and programming, and revisit the principles and my examples from time to time and see if they start to come into focus. When you create a design or see a system that is already designed, see what principles you can identify. Have fun with it.